Welcome to the lecture on the Stellar Consensus Protocol. So, in this lecture, we will discuss a very different kind of consensus protocol. So, we have seen a lot of consensus protocols up till now. We have seen Paxos, Raft, we have seen Bitcoin, Ethereum. So, Stellar is different, it is more scalable, it's also new. So, Stellar is a 2016-18 protocol. So, we will see it's much newer, much faster, much more complicated as well. So as we have discussed, there are two kinds of blockchains. There are permission blockchains which are easy, systems such as Hyperledger for instance. Then we have permissionless blockchains, systems such as Bitcoin and Ethereum, where you don't need permission, but because of probabilistic or rather cryptographic guarantees, it is possible to ensure that there is only a single version of the chain that is accepted. In the case of a permissioned system such as Hyperledger, all the participants are known, they have login IDs. So all of them can be authenticated. And if they turn malicious, some action can be taken. So it's clearly not suitable for open membership, as we have seen, right? So it is not that anybody can join at any time. So this is more like a corporate intranet kind of system, right? So what makes blockchains really interesting is permissionless systems, of which Bitcoin and Ethereum are prime examples. So we can use them to implement cryptocurrencies, which is by far their biggest selling point. So the key point that all of them use, including any protocol which is tolerant to Byzantine faults, and that includes in this case Ethereum and Bitcoin as well, is that in the case of Byzantine faults, nodes can behave arbitrarily and maliciously. And furthermore, malicious nodes can kind of cooperate with each other, collaborate with each other, and send messages to confuse the rest. So if you look at our classical fault tolerance result, which is there earlier in this lecture series, you will find that Byzantine faults, if we have 3f plus 1 nodes, we can tolerate at the most f Byzantine failures, and then also it takes a lot of time. Kind of takes n factorial time to still come at an agreement, right? So still come at a consensus, it takes that much of time. But nonetheless, with 3f plus 1, the maximum number of Byzantine failures we can tolerate is f, not more than that, because more than that, the system is not guaranteed to complete, right? So in this case, 2f plus 1 nodes make a quorum. So what does that mean? All of them need to be correct, and all of them need to agree on the same value, agree on the same consensus value, regardless of the rest. So we can think of them as having a quorum. Even a classic centralized system, where if the centralized server is guaranteed to be honest, then all that you need to do is you need to send a message to the centralized system, get a reply, and insofar as all the nodes are concerned, the centralized system is the quorum. So what is a quorum in this case? A quorum is a set of nodes who have to accept your right and who provide you the value of a read. So of course they may collaborate among each other to provide you the value of a read, but at least if they are correct, you know that the entire system is correct. In the case of classical Byzantine fault tolerance, 2f plus 1 nodes is the minimum that you should have for a quorum size to ensure you are getting the correct answer back. So some new ideas have been proposed, such as Stellar and Ripple. So they use a very interesting new concept known as Federated Byzantine Quorum System. So Byzantine we know, Quorum we know. What is federated? Well, federated basically means like a federal, federation of states. So in a sense, it is like it's a hierarchical network or a hierarchical setup where different groups kind of elect their value, and then ultimately one of them is chosen. So you can think of the fact that the entire network is broken into different subgroups, and each subgroup in a sense elects in a certain sense its value. But what are the key advantages? So why have Stellar and why not have others, right? Why are we discussing it. The biggest advantage of Stellar is that the participants are not known, right? So, unlike many of the other protocols, which includes Bitcoin and Ethereum, where if at least the participants are known or the network is known or some multicast ID is known where you can send it to all the participants. In this case, the participants are genuinely not known. They can join and they can leave at will. There is no need for all the nodes to participate in a consensus protocol. This is key because what was happening in Bitcoin, for instance, is that all the nodes had to participate. In fact, 51% had to agree. So we needed a lot of participation, and only then was a block getting ratified. But in this case, that's not the requirement at all. This makes a heaven and earth difference. Furthermore, every node chooses whom to trust. So think of it as a private quorum in the sense that every node only knows a few other nodes and it chooses that I'll trust only those nodes and not the rest. So of course there are some restrictions. This protocol is not as general purpose as Ethereum, for instance. But again, there are advantages in the sense that this relies on local knowledge. It doesn't rely on global knowledge. You don't have to know all the nodes. You know a few and you trust them. So this is modular, scalable, and ultra fast. So let's first discuss some background and assumptions. So let's say the universe of nodes is V. This is a set of all the nodes. A node is correct if it executes as per specifications, right? So it is correct meaning it's correct. So it is the dictionary meaning of correct, which means as per laid out specifications, the node executes. If a node is either correct or it just fails, without sending any malicious messages, the node just fails. That's okay. That is fail stop. It is not a Byzantine failure. It's a fail stop failure. Then the node is dubbed honest. Right. So where are we? We are at the point where we say that a node is correct, which means it executes as per specifications, or we are saying that it can have a fail stop failure but will not send any malicious message. So then we will say that the node is dubbed to be honest. The rest of the nodes we say are faulty. So the Stellar protocol can work in an asynchronous setting. It is just we can't make certain guarantees. But if it's a partially synchronous network, which is often the case that the clocks are loosely synchronized, we can make more guarantees as we will see. So what happens is we assume periodic clock synchronizations known as a global stabilization event. And when the clocks are synchronized, it's a global stabilization time. All the messages have a bounded amount of delay and the clock skew is bounded, right? So that's important. Now, the messages themselves have a bounded amount of delay, a bounded degree of delay, and the clock skew itself between two clocks is bounded. So this is a partially synchronous network and most practical systems are partially synchronous. So there's nothing to be, surprised about this. It's not a wild assumption at all. So what is the key idea? So the key idea is that every node trusts a set of nodes. So if this is one node, you create a quorum slice. So this could be a quorum slice. This could be a quorum slice. So of course, a node has to be a part of the quorum slices. So you can say that in this case that there are three quorum slices and the node is a part of all three. Of course, because every node has to trust itself and a node can be a part of multiple quorum slices, right? As you can see over here. And a quorum slice informally is a set of nodes that the node trusts and a node is a member of all of its quorum slices, right? So this is very easy to do in the sense if you have a large network, you can say that the node will trust its system administrator and if there could be multiple system administrators, it could trust them. That could be one quorum slice, or a node could trust the machines of some colleagues, or a node could trust the machines of some students. So then, as you can see, we have three quorum slices over here. We are not restricted to one. A quorum is defined as a set of nodes, right? So a quorum is a set of nodes, a very important concept. Every node that is a part of a quorum will also have at least one of its quorum slices. So let's say V is a part of a quorum and it has three quorum slices, right? Either QS1 or QS2 or QS3 has to be a part of the quorum, right? So either QS1 or QS2 or QS3, any one of them has to be a part of the quorum, right? So what's the idea? The idea is that a quorum is a set of nodes. You take any node in the quorum, you will have at least one of its quorum slices that is fully contained within the quorum, right? So let's say if this is a node and the node could have multiple quorum slices. So we are not concerned about that. But there is at least one quorum slice which is fully contained within the quorum. And this is the case for all the nodes. So this is a quorum. So what does this mean? Right? So intuitively, what does this mean? So a quorum slice basically is the set of nodes that a given node trusts. Alright, so that is a quorum slice. Now the moment we have a quorum and we consider every node in the quorum, so you consider this node. If one of its quorum slices is within the quorum, then at least what can you say? You can say that if the entire quorum takes a decision, if all the nodes within a quorum take a decision, then you know that at least one of its quorum slices also has taken the decision. And given the fact that the quorum slice is trusted, the node can use that fact to make a decision. Yeah. So this node can use this fact, some other node, this node can also use this fact because it will have its quorum slice, at least one which is fully contained within the quorum. So this basically means that if the entire quorum takes a decision, whatever be the decision, right, in the case of consensus, for instance, then all the nodes within the quorum can have some degree of relief. The relief is that some set of trusted nodes, which is at least one of their quorum slices, has been a part of it. So this gives a degree of sanctity to the decision, which we will see to be very important. So clearly in this case, the notion of the quorum is the most important concept. So now assume that for the time being, all the faulty nodes are not lying about their quorum slices because faulty nodes are Byzantine faulty, right? So they in principle could lie about their quorum slices. Let's assume this is not happening, but even if it does happen, it's not an issue. So let us give an example of quorums and quorum slices. So let's say V1 has one quorum slice, V1, V2 has two quorum slices. As you can see, it's a part of both V3 and V4. So there are some trivial quorums. So let's say V3 is a quorum in itself because it's the only node and V3 is its quorum slice which is fully contained. Fair enough. V1, V2 is a quorum. Well, why? Because V1's quorum slice, V1, V2 is fully contained here. V2 has two quorum slices. One is not fully contained, but V1, V2 is fully contained. And then, of course, the universe of all the nodes is also a quorum because all the quorum slices will definitely be in it. So, as you can see, for a system with different quorum slice definitions, multiple quorums are possible. So, now we need to come at some basic requirements that we defined what is a quorum slice, what is a quorum. But now let us see when is it that you can guarantee consensus in this FPQS federated Byzantine quorum system argument, right? When is it that consensus can be guaranteed? This is by and large the most important requirement. So as I have said over here, you can have a lot of quorums. So it is saying you take any two quorums, Q1 and Q2. All pairs of quorums have to have a non-empty intersection. Furthermore, one of the nodes within that intersection has to be correct. All right. So what's the idea? The idea is you take all the quorums in the system, intersect them. The intersection has to be non-null. And furthermore, in the intersection, you need to have a correct node, which means they need to intersect at a correct node. So we'll discuss the insights later. But the most important point here is that when you are designing a system, in fact, the trickiest aspect of designing a stellar network is to basically choose these quorums, right? is to basically choose these quorums such that this condition holds. And furthermore, let's say I create quorums and then there is an intersection. How do I know whether, let's say, the three nodes that are intersecting, all out of those three, at least one is correct? Because I may not have control over the runtime system. Well, that part is correct. If I do not have control, of course, I will have to go to other algorithms, the way that we have seen in Ethereum, Bitcoin, and others, which don't have this restriction. But many a time, you would have some nodes which are more fault tolerant than others. For example, the machine of the system administrator, and so on. And if we have maybe four nodes in the intersection, we have to look at probabilities. So the probability of all four of them developing a Byzantine fault might be very, very low. And this is something that we want to hedge against while designing our quorums. So what will the correct node do? So here is the fun part, right? So the correct node will essentially ensure that there is a common agreement or consensus across all. Well, I use the term quora here for the plural of quorums, but I should use quorums because that is what we have been using. So the key point is that if there is one correct node in the intersection, and if, let's say, one quorum has decided something, so what is the advantage of a quorum? A quorum decides a consensus value. Now, if every other quorum in the system has an intersection with it at a correct node, later on, let's say, if another quorum tries to decide something or tries to decide something which is the opposite of what Q decided, right? If Q dash tries to decide something which goes against what Q has decided, then the correct node at the intersection is actually going to stop it, right? You can never rely on faulty nodes, but the correct node is going to stop it, and it's going to say that, look, a quorum has already decided something and you are going in an opposite direction, so don't go that way. And the same holds for all the other quorums. So that is why quorum intersection is important. So in other words, in this case, all that you have to do or you need to do is to convince a quorum to accept a value, then you are done. If the quorum is small, you don't have to broadcast the message to all the nodes. All the nodes will ultimately get it. Few more definitions. Two nodes V1 and V2 are said to be intertwined if they are both correct. So that's important. Whenever we are talking of nodes with some decision making capability, both of them have to be correct. That is necessary. Furthermore, every quorum that contains V1 intersects every quorum that contains V2 in at least a correct node. So this is slightly uh, this is slightly specializing the definition to a pair of nodes that, look, two nodes are intertwined. Number one, if they are correct, and number two, if, let's say, every quorum that contains V1 will intersect every quorum that contains V2 at a correct node, which is a specialization of the definition, but we will see why it is being done like this. Let us now define an intact set. So the definition of an intact set is quite crucial for the rest of the paper as well as for the proofs. So what we do is, let's start with a federated Byzantine Quorum system, FBQS, and let us project it to set I. So let's see what that means. So informally, what it means is we consider only those elements in S that belong to set I. So S projected to I basically means, if I look at the vertex level, so for every vertex, I take a look at all the quorum slices. So SV is basically all the quorum slices. So I consider each one at a time. So if Q is an element of this, I only consider those elements of each quorum slice that are also an element of I, or basically I compute an intersection between Q and I, right? So basically what I do is that, if, let's say, this is my full set S, and I have this I as the set on which I'm projecting. So what I do is I take a look at every vertex V, right? And for this vertex V, I take a look at all of its quorum slices. So let us say the vertex V is over here, and these are its quorum slices. I only consider that part of the slices which lie within I, right? So this is the projection. So a set I is an intact set. Such kind of a set I is an intact set if it follows two properties. The first is I itself is a quorum in S. So what we do is that we take the federated Byzantine quorum system S, and in that, let's say I choose one quorum and that quorum is I. So I call that I as an intact set if all pairs of vertices within I, let's say this vertex and this vertex, are intertwined, right? Are intertwined. So go back to the previous slide to understand what intertwining means, which means both the nodes are correct and they are intertwined in S projected to I, which basically means that there is some quorum slice of this which completely lies within I, and there is some quorum slice of this which completely lies within I. And the fact that they are intertwined basically means that they intersect at a correct node. So, of course, the way that I have drawn, they are not intersecting, but you get the idea. So, the idea is that if I consider, if my new universe, everything is limited to the set I, and for every quorum slice, if I only consider those elements that are a part of set I, then I will consider I to be an intact set if I was a quorum in S, right? So, that is the first condition. The second is if I project S to I, in the sense I only look at all the nodes and quorum slices of S that have a non-zero intersection in I, then any two pairs of nodes in I are intertwined in this projection. So this basically means that this is kind of a self-contained set. That's the reason it's being called an intact set. It's a self-contained set where if I take any two nodes and I basically take their quorum slices, then there is an intersection at a correct node. And of course, these completely belong within I, right? So it's like a self-contained universe. So this is an intact set. So let us understand a little bit more and look at a few theorems with regards to intact sets. So why do we look at intact sets in the first place? The reason we look at intact sets in the first place is basically because intact sets can reach a consensus, right, using the stellar algorithm, right? Independently, intact sets can reach a consensus. And of course, if the entire network is an intact set, then the entire network can reach a consensus. So the first theorem is like this, that let us consider a quorum U1 and a quorum U2, and let's say both of them intersect with the intact set, right, with an intact set I. If that is the case, then U1 intersection U2, which is this part, this will have some intersection with the intact set I, in the sense it will be non-null. So this is an important result that is used in the proofs of the stellar protocol. So I would encourage all of you to take a look at the papers and understand the proof of the protocol. But the basic idea is that if, let's say, there are two quorums which intersect the intact set, then the intersection of those quorums also intersects the intact set. All right, so the intersection is not disjoint. Furthermore, if I take two intact sets, for instance, so this is one intact set, this is one more intact set, and let's say that they are intersecting, right? So they are not separate, these are intersecting, then they are closed under union, which basically means that if there is a common node between them, then the union of intact sets is also an intact set, right? So this basically means that in any kind of a network, unless a node is totally disconnected, if we have intact sets of this type, then essentially all of this is an intact set and all of this can reach a consensus. So basically the only intact sets that will not reach a consensus along with the rest of the intact sets is if something is totally cut off, right? So what does it mean to be totally cut off? In the sense it doesn't have any intersection with the rest of the intact sets, right? So that is when this is totally cut off, because what we also get to see is that, by the first theorem over here, let us assume that there is some other intact set like this, such that there is an intersection here and an intersection here. So what we then see is that the intersection of, these two quorums over here has to be non-null, right? So that part is clear, that these two have to intersect, and if they intersect, the intact set will further grow. So that's the reason either you have a separate kind of a disconnected component over here, right, which does not intersect any intact set. So then of course, it is separate. Otherwise, if there is any intersection, you can consider this to be a larger intact set, and that can independently reach consensus as per the stellar algorithm, which is something that we will see. So let us now look at the idea of non-blocking consensus. So I'll discuss what is non-blocking over here. But basically, in the presence of nodes that could have Byzantine failures, so let us look at this for an intact set. And given the fact that we have discussed this union and intersection business over here, let us consider a maximal intact set I, where clearly we can't grow it further, in the sense there is no other intact set with an intersection such that we can grow it. So the scope of growing it is not there. So it's a maximal intact set. So what we say is that these four properties will be satisfied by stellar, and in fact should be satisfied by any consensus algorithm that deals with such kind of intact sets constructed in this manner. So what are the properties? The first is integrity. So integrity basically means that no correct node decides twice. So this follows from the definition of consensus, that if you are a correct node, once you have said that this is the consensus value, that remains. You don't change your mind. Agreement again follows from the definition of consensus. It basically means that no two nodes decide differently. Of course, weak validity, which basically means that if all the nodes are honest, then the value that is decided is one of the proposed values, of course. So in this case, the idea basically is that if we are looking at honest nodes, then of course one of the value has to be one of the proposed values. So this again follows from consensus. What doesn't follow, but what technically makes sense, is that let's say there are no malicious nodes, right? Or all the malicious nodes just stop. Then the protocol is guaranteed to terminate, because in this case, this will not be against the FLP result, because what does the FLP result or protocol say? We cannot guarantee termination if any malicious or faulty nodes are active, right? But the point is that in this case, malicious and faulty nodes, if they are not active, you should be in a position to guarantee termination of the consensus algorithm. So the first three kind of follow from consensus, and the fourth one follows from the fact that you would like to ensure a minimum amount of liveness in the system. So we have these four properties, which are the consensus guarantees you would like to have, at least for maximal intact sets. So the key part of the algorithm is federated voting, which draws inspiration from two-phase commit. So in this case, we have two phases. So it's called vote and deliver, but later on we will see it's also called prepare and commit. It doesn't matter. There are two phases. So I would like to request the viewers to look at two-phase commit, to also look at the Paxos algorithm, because that also has two phases and it is quite similar to this part, right, where you vote and you deliver. So for the correct nodes, federated voting would like to ensure these four properties. So this is also known as reliable Byzantine voting. So the reliable voting basically means what? So in this case, mind you, voting is not consensus. Voting is a process which provides some safety guarantees, very little liveness guarantees, but let's nonetheless see what it is. So the idea is that nodes vote for a value, and let's say if a quorum successfully votes for it, then it is delivered. So there is no duplication, in the sense every correct node would deliver at most one voted value, right? So basically, as I said, delivery is the second phase, voting is the first phase. So in the second phase, you deliver at most one voted value, not more than that. Then you have totality. If a node in I, where I is an intact set, delivers a voted value, every node in I delivers a voted value, right? So basically, what does that mean? It basically means that you have, so this is a liveness guarantee, which basically says that look, if one of the nodes, one of the correct nodes in an intact set terminates and delivers a voted value, then all the other nodes also will terminate. So this is a liveness guarantee. The first one is of course a safety guarantee. So consistency basically means if two intertwined nodes, which is like any two nodes in an intact set because all pairs are intertwined, if they deliver A and A dash respectively, then A is equal to A dash in the sense it delivers the same value. So this is just a sophisticated way of saying that all the nodes in an intact set deliver the same value. So the way that it is written, because I've kind of paraphrased what is there in the paper, that if two intertwined nodes deliver A and A dash, then A is equal to A dash, right? So which basically means that once a node delivers, everybody delivers and everybody delivers the same value. That would be the sum total of 2 and 3. So this is like what you would like your federated voting algorithm to ultimately satisfy. And then of course we have validity. So validity basically means that, so this again is, this was again a, a safety condition. So this is one more safety condition, the last one, which essentially says that look, you deliver only what you have voted for, right? So you don't deliver something else, you deliver only what you have voted for. So if you look at it, so no duplication was what? That on only one of the values, once a node delivers, it can't kind of vote for any other value, or it can't also deliver any other value. So then this was a safety condition. The last one, as we have just seen, is a safety condition. And the third one is also a safety condition, basically because it says that all the intertwined nodes in an intact set, which is all the nodes, deliver the same value. So the liveness condition is basically like this, that if one node delivers, everybody delivers, is the only liveness condition. So what we see over here is that federated voting is again, taking some aspects of consensus. It is again, of course, it has a different liveness condition as compared to this slide. But the idea basically is that the first slide was consensus for intact sets, and this is a property of federated voting, which will ultimately take us towards consensus for intact sets. So federated voting as such is a step. So FV is a step, and FV will take us towards consensus. So then, what do we have now? So what we have now is, let us look at the federated voting protocol. So as I have said, it's a two-phase protocol where first you vote and then you deliver. But again, you are guaranteed to deliver only a single value. And the entire intact set either delivers or does not deliver, right? So we have this liveness guarantee. And if it delivers the same value, right? Otherwise, it doesn't deliver at all. And of course, if you, in the rare case where everybody votes for the same value, it's only that value that gets delivered. So the way that you need to think about it is that it's a two-phase algorithm of vote and deliver, where the voting process may actually not successfully complete. If that is the case, nobody delivers. But if it successfully completes, then everybody is ultimately guaranteed to deliver the same value. So this is essentially the crux of federated voting, which the algorithm on this page will convince you that it works. So what we do is that we do a federated voting on the set of all vertices, and a tag essentially indicates a round, because the way that the master protocol works is that we have many rounds of voting. We don't have just one round of voting, but we have many rounds of voting, and the tag indicates the round of voting. Then we have the state variables voted, ready, delivered, all start with false. So let's start with the vote. So of course, if any node wants to vote for a value, it can initiate, or we will see that there are other conditions also, but at least let's say that a node decides to initiate, that it needs to vote for a certain value. So for that specific round, right, for that specific tag actually, if it has not voted, then it will vote only once. So basically the idea is that for a given tag, so I'll use tag and round interchangeably. So for a given tag or round, you can vote only once. The moment you vote, the variable voted becomes true. Then you send the vote message to every vertex, including yourself, in the vertex set. And what would that include? That would include the tag number and that would include the value that you voted for. And mind you, you're allowed to do this only once, right? Not multiple times, only once, because of this variable over here. So the moment you receive a vote TA message, right? So moment node V. So node V is always the node that is processing, either sending or receiving. The moment it receives a vote TA message from every node of a quorum that it is a part of, right? So here the idea of a quorum is coming. So you can go several slides back, but the basic idea of a quorum was that every node in the quorum, of course, belongs to the quorum, and one of its quorum slices definitely belongs to the quorum. So if a quorum votes for V, and of course we have quorum intersection and so on. If it is not ready, so again we have a ready variables. If I'm not ready, which means ready is false, I set ready to true. And then I send a ready message to every other node, including myself. So go back to two-phase commit. In two-phase commit and Paxos, we were doing something quite similar. So the first round you send vote messages, right? Once you get vote messages from a quorum, right? So once you get these, vote messages from a quorum, then what you do is that you begin the second phase and then you send a ready message to everybody else, including yourself. Okay, in the second set, so here is also a fun part that the ready message is also sent if a V blocking set. So I'll describe what is a V blocking set. So let us say this is vertex V and these are its quorum slices. A V blocking set is a set which overlaps with every quorum slice of V. So it is like this. This is a V blocking set. So if I am a node V and a V blocking set, which as I have said, these are my quorum slices. So a V blocking set pretty much overlaps with every quorum slice. In a sense, it has a non-zero intersection. So if it sends a ready message to me, right? So if it sends a ready message back to me and I am vertex V, then what do I know? What I know is that at least, for all my quorum slices, one of the nodes has changed its status from not ready to ready, and it will not change its status ever again, right? So from not ready, it has become ready, which means it's done, right? It has made up its mind, it has voted, as well as it has changed its status. So then whatever ready message it sends, so mind you, this may be different from what I originally voted for, right? It may be, this value of A may be different, but that's okay. It means that whatever I originally voted for, didn't find adequate support. But now given a V blocking set, which means pretty much one entry from every quorum slice of mine, if that has committed, it has changed its state from not ready to ready. So that will remain. It's kind of final. So what I will do is if I am not ready again, because I change my state only once for a given round, I change my state from not ready to ready only once. So the moment I do that, if I'm not ready, I become ready, and then again I broadcast a ready message to every vertex. So what you see over here is that a ready message can be propagated right? Of course, the first node to send a ready message has to receive votes from a quorum. So that is given. But after that, a ready message can be propagated if a V blocking set has sent the same ready message to a node V. And in this case, of course, it can be different from its voted value, but it will still propagate it. And then what happens is that for node V, if it receives ready messages from a quorum, which means a full quorum is sending a ready message, again similar to two-phase commit, that if it has not delivered, then it will set delivered to true and deliver the message. So this is basically what delivery in an intact set means, which means it has passed both the rounds. So of course the first round is not guaranteed to terminate, mainly because it's possible that an entire quorum may not agree. You have a 50-50 situation, or even worse, when multiple values are being proposed. So that is why I said the first round is not really guaranteed to terminate, and we will see timeout mechanisms for that. But assuming it does, then of course you can guarantee beautiful things. And what you can guarantee is that the same value is delivered. Number one, right? So you can guarantee everything that federated voting guarantees. No duplication. You can clearly see that you deliver only one voted value because only once your state changes from not delivered to delivered. If a node in I delivers a voted value, well, it's guaranteed that it has support of a quorum. So no other value can be delivered because of quorum intersection, right? So you take any two quorums and you'll have one correct node that is in common, and that cannot lie. So given that it has already committed to a given value, it will keep that commitment. So nobody else can deliver anything else. So that proves property 3 as well. And furthermore, if all the nodes vote for a single value, then that has to be delivered, because if you see our algorithm, there is no way to introduce any other spurious value, extraneous value in the middle. So this is like a two-phase commit where, as I said, the first phase need not finish, but if it does, then you have these beautiful safety and as well as liveness properties of federated voting. Now let's look at some of the insights. So the insights anyway we have discussed, but still I am repeating them. The first ready message is received only after the same vote message or the vote message for the same value is received from an entire quorum, is received from a full quorum. So only when a full quorum sends a ready message to a single vertex V, and then so then only so I'm sorry, only when a full quorum sends a vote message for the same value, and a vertex V receives all of that, then it initiates the ready message, and then of course it is propagated via the V blocking sets, right? So via this line over here, it is propagated. Termination is not guaranteed, because if it would be, that would violate the FLP result. And in particular, the first phase is the one that causes the problems primarily. However, once a message is delivered, what does that mean? Well, what that means is that a full quorum has voted for the message. So it's not going to vote for any other message. So that is being ensured with this line, right? With this. So if it's not going to vote for any other message and no other message can be delivered, so we are at least assured that it's only this message which is going to be delivered. And of course, for all the correct nodes, they will get the delivery in finite time if we assume bounded clock skew. So we assume that we have a partially synchronous system and all the nodes are active, in the sense executing this algorithm. Then within a finite amount of time, which can also be made bounded also, if one message is delivered, all the messages will be delivered to the intact set. So let us now take this to the level of a ballot, right? So let us now create a consensus protocol, or rather a blockchain out of this. So what we want is that we want to use federated voting as the primitive, and then we want to build on top of it. So let us introduce the notion of a ballot, where a ballot is a tuple of a positive number which keeps monotonically increasing. So this is the round number. the tag that we discussed, and x is the value that is being voted upon. So we say that b is less than b dash if either the number b dot n is less than b dash dot n, or if the numbers are the same but the value is less than that. So the value is used as a tiebreaker only when the numbers are the same, otherwise we go by the number. So two ballots are said to be compatible if their values are the same. So that makes sense. This is the symbol that we have for compatibility, and two values are not compatible, again this symbol, if the values are not the same. So the term that we will use to assume that b is less than equal to b dash, in the sense the numbers are less than equal to that, right? So it will follow the same notion of equality and less than over here. So if we have this and the ballots are incompatible, right? So it is less than equal to this and the ballots are incompatible, we write b, right? So hopefully this is clear that if the ballots are not compatible with each other, then we basically write that, and let's say one is less than equal to the other, then we write it in this fashion. So actually, we can write less than as well, because if the ballots are incompatible, we will never have strict equality. But uh, well, we could have equality in terms of numbers, but the values will not be the same. So that is being captured with the less than equal to over here. But nonetheless, the term is clear that the moment we have something like this, it is essentially indicating an incompatibility. And along with that, it is also indicating that one is less than equal to the other in terms of these numbers that we have defined over here. So now let us discuss an abstract consensus algorithm. The reason I'm using the term abstract is basically because it assumes infinite resources, which is not the case. So we will discuss a version of this algorithm that uses finite resources. But at the moment, let us proceed with the version that uses infinite resources. So let us say that specific to each ballot, we have a federated voting process. So given the fact that we don't place any bounds on this array, in principle, this could be infinite. So that is why I say it's an abstract algorithm or a theoretical algorithm, but very soon we will place bounds on it. So an array of federating voting processes are in ballots. We maintain two state variables, candidate and prepare, initialize them to 0 and null. And of course, the first round is round 0, and this keeps on increasing monotonically. So here again, we will have, two phases. So we have taken a lot of inspiration from the two-phase voting protocol. So here also we'll have two phases in the ballot algorithm. So this is the consensus algorithm. So we start with the candidate. So the candidate is basically a tuple of round 1 and the value x that is being proposed. So as you can see, it is the same value that is being proposed. So here is what we need to do. So here is the fun part of where the federated voting aspect is being used as a function. So for all the ballots, for all the values of b dash, which are less than and incompatible with candidate, we have to ensure that everybody agrees that you vote for false. So you vote for false basically means that all of those ballots and their values are voted to be false, in the sense those ballots everybody agrees that we will not accept it, or this will not be your consensus value. So you are essentially voting false on them. So this basically means that whatever ballots are not compatible with your candidate and which have a lower number, you first invalidate all of them, and then only we try to validate this candidate, otherwise we don't. So this also makes sense. So essentially you are cutting out the possibility of any candidate which has a lower number than you, which is less than and incompatible to you. Because if it's compatible, you don't care, it's the same value. But if it is incompatible, you are cutting out the chances of it ever being chosen as the consensus candidate, because you are waiting for all of them to vote false. Let us now look at the second part. So now, what have we done? We have said, we have given an order that all the ballots which are less than and not compatible with the current candidate have to be invalidated first. So when all of them are invalidated, so of course here I'm changing the connotations. So well, B is always our current candidate and B dash is always the other one. So in that sense, it still remains the same. But of course, it should be clear that these are separate algorithms. So when every B dash which is lower and incompatible with B, its ballot delivers a false, which means that it is successfully invalidated. Right? So again, as I said, this process is not guaranteed, because if this process was guaranteed, we would have used this as our consensus algorithm. But once all the lower and incompatible ballots are successfully invalidated, and we have not prepared a ballot which is as high as the current one, all right? So that is also important, that it is not as high as the current one, because B is always the current ballot. So then what we do is that we set that to prepared. So this is the same as if not voted, then vote. It's the same logic. And what we see is that if, let's see, so this is prepared, right? So B in this case is basically a ballot less than which we have received all the false messages. So the point is we set that to prepared because that is the largest value of the ballots that we have prepared. So what does preparing in this case mean? Preparing in this case means that all the ballots which are lower and incompatible, all the B dashes have been invalidated. So once we have such a B, we set it to prepared if that is the largest such value. And then we look at the relationship between candidate and prepared. So as long as we have prepared a bunch of ballots which are at least equal to the candidate or greater than it, then we are fine, then it's a valid candidate, which means the candidate is good to go. Because if this is the level of the candidate, the round, and if this is the level of prepared, and if less than prepared, everything which is incompatible has been invalidated, then it also means that anything less than a candidate also has been invalidated, right? And basically the candidate is good to go. So we set candidate as prepared, we set it as prepared, right? Because it is, of course, you're assuming that the same value is being proposed, right? So candidate and prepared are compatible. And the reason that I say that is basically because the same node will only propose a single value in this case. And if, let's say, less than prepared, everything is invalidated, less than candidate also holds. So we set candidate as prepared. So in the sense we kind of boost its rank up and set prepared, take the value of prepared and set that as candidate. And then I set ballots candidate dot vote true. So what does this mean? So what this basically means is that once I am sure that all lower and incompatible ballots are all invalidated, then I try to convince everybody that look, here is a candidate and you vote true for it, right? So this kind of begins the second phase. So when all the ballots have delivered a true, in the sense all of them agree on the candidate, we decide that it is true and this finishes the consensus, right? So this means consensus has been achieved. So once one true message is delivered from our earlier theorems, we know that the rest will also be delivered because of the property of intact sets. So we don't really have to wait for all the delivered messages to reach their destinations. The moment we get one, we declare victory and we say consensus has been achieved. Right? So as you can see, we use federated voting, and even the top level algorithm is also federated voting. So essentially it is basically a two level hierarchical federated voting, where our aim is to kind of cancel out all the ballots with a lower number which are incompatible. Once they are all cancelled out, then what we do is we say that look, here is the candidate. So first we vote false, which this is cancelling. This process is cancelling, and then we vote true, which basically means now all of you agree on this candidate. So as I said, the process of federated voting is not guaranteed to complete. So it is not guaranteed to complete, which basically means that there could be, the first phase could get stuck. So that is why we need a timeout mechanism. So here is what we do: assume a node V and a quorum U where V is a part of the quorum. If let's say for all nodes in the quorum, right? So all nodes in the quorum that V is a part of, there exists a ballot BU such that. So BU is a ballot which is associated with U. And what is U? U is a node in the quorum. So let me do this. This is the quorum. This is a U with it. And associated with it is a ballot BU. So there has to exist a ballot BU such that the current round is less than the round of the ballot. So BU dot n. We have either received a vote or ready message for this ballot with a true, right? Or we have received a voter ready message, but for some ballot B dash, which is false, where B dash is defined as follows. So which basically means that there is an open interval that ends at BU. In a sense, this is BU, and these are all the ballots which are incompatible. I'm sorry, which are less than it. So there is an open interval in the sense it doesn't contain BU, but it contains all of these. So as long as for each of these, right? So for each of these iterated is B dash. So as long as for every B dash which is a part of this open interval, we have received a false in the sense that this has been invalidated. So if that is the case, right? Then what we do is we realize that we are in trouble. So why do you realize you are in trouble? Well, you realize you are in trouble because a ballot exists whose current round is high, which is higher than the round of the current node, which is V, and V is a part of U, right? So it has clearly seen other ballots whose current round is quite high. That is the first point, right? And the other is it has also received messages from them to either confirm the correct ballot or basically a prepared message, so there is basically for all the ballots which are lower than it, it has received, prepared, these prepare messages. So vote and ready are part of that prepare. So I'll show you where, one second. So they are part of this, right? So vote and ready are part of this federated voting process. So as a part of this federated voting process, it has received lower number ballots from an open interval which is less than BU, saying that look, all of you are false, right? So either it has received a vote of true for this, or it has received a vote of false for these, which basically means that there is some ballot which is active at a higher round, and all the other ballots in the quorum are higher. They have also been sending messages, and we have gotten those messages, which means that I am somehow left behind. So what is the sum total of this argument? The sum total of this argument is that I have been left behind, right? So I am behind other nodes, I am left behind. So what I do now is that I increment my round. So I take all the nodes in the quorum and I take the minimum n value, which is the minimum value in their ballots that they are sending, and I set that to my current round, and I also start a timer, right? So this is the timeout mechanism that I was talking about. But what you do is you realize that, given that all the nodes are not making progress at the same rate, a node basically realizes that it has fallen behind, mainly because the round numbers that all the nodes in the quorum, including it, are using is much higher than the value of the round state variable, its round state variable. So that is why it increments its round and starts a timer. So at timeout, what happens? So basically, you can see the paper. So in detail, they have explained what it means, what is the connotation of the timer. So here, of course, so then what you do is that if you have already prepared something and sorry, if the prepared is uninitialized, then you start. This is similar to the proposed function, right? So I'll show you the proposed function. Here is what you do. You vote on a candidate. You basically prepare. So you increment the round plus 1, and with candidate's value, you start. Otherwise, if you're already prepared, then, so as I said, it is never the case that you propose different values. So whatever value you prepared with, prepared.x, you just increment the round number and set that as the current candidate. Then, as you can see, the second line is exactly the same as this line over here, which is you go forward and invalidate all the lower numbered ballots. So if I were to summarize, here is the key idea. You take all the lower numbered and incompatible ballots, you invalidate them, and then once that is done, you try to make everybody agree on the candidate. That's the idea. And if, let's say, for some reason the protocol gets stuck, which it can, because anyway federated voting liveness is an issue, nothing, you just set a timer. So the timer will basically ensure that the system stabilizes, in the sense that all the messages we have sent are received, and after that you just increment the round and start afresh. So here are some basic properties of this algorithm. So the basic properties would be like this: if some node decided on a ballot, it means some other node must have prepared it. That has to be the case, because after all, there has been a flow of information between the nodes, right? So you see the algorithm, you can't decide a value out of thin air. So if a ballot has been decided, it must have been prepared. Now, if a node has prepared a ballot, some node must have proposed the value, right? And again, this can be the same argument that we have a continuous information flow, so someone must have proposed the value. All the nodes in the intact set decide the same value. So this we have been discussing for quite some time now, that it is not possible for the nodes in the intact set to decide some other value. And this is a direct result of the federated voting protocol, that because of quorums and quorum intersections and so on, given the fact that all quorums intersect at least at a correct node, and the correct node can only decide once, right? And it for the same round, I mean, it actually cannot prepare different values, right? So that is not possible, right? If you take a look at this algorithm over here. So basically, the key point here is actually quite clear, that for any node, the information flow is maintained. And so I'm not discussing the timeout, etc. Fact, but given the fact that quorum intersection holds, it is quite obvious that the single correct node that is there, that will not give confusing messages to the both the quorums that it is a part of. So sadly, even though this algorithm works, we need an infinite amount of state, because the state of all the ballots and all the tags or rounds has to be maintained, which is not in the best interest of the algorithm designer, because it will lead to an unbounded amount of state, possibly infinite. So we have to work on a finite version of the protocol, where the idea is that we don't maintain an unbounded amount of state. Instead, we have minima and maxima and so on. So we remove entries, there is some garbage collection, right? And also, we don't maintain all the messages and all the state, but we maintain a subset of the full state, or a subset of the full set of messages. And anything that we feel is beyond the range, in the sense should not be maintained or can be inferred, that is removed. So again, we'll have some new terminologies. As I said, terminology keeps changing, but thankfully it still remains a two-phase algorithm. Where, so last time we had prepare and decide. In this case, we'll have prepare and commit. Same thing. And so basically, we have used many terms: vote, deliver, and now it will be prepare, commit. But again, in a prepare commit is to kind of refer to the finite version of the algorithm. Same concept. So the new FV algorithm, the new federated voting algorithm, which is finite, works like this. So what happens is that if you look at when you're preparing a ballot, right, you see what is the largest ballot that you have voted for. If it is less than B, and if this is clearly a higher number ballot, because you want this to be monotonically increasing. So if you have not voted for the current ballot or for later ones, then you set max voted prep to B, which is also what we were doing previously, right? So in this case, what you do is that you say that, look, I will keep on voting. I don't have an issue. But the thing is that I'll only vote for ballots with monotonically increasing numbers. Then I will send the vote. So the message that I will send is prepare prep, and max voted prep is just what I voted for, which is basically what I proposed, the ballot that I proposed to all the nodes. So this part is the same. It is like sending your basic vote messages. So then what will happen is if there exists a maximum ballot B, right? So again, this is the next part. So if there is a ballot B which is greater than max voted prep, and if every node U in the quorum that contains V has sent vote prep BU, where BU has the following property. If there is any B dash which is lower and incompatible to B, it is also lower and incompatible to BU, right? So which basically means, that if this is B, BU is somewhere over here where everything is lower and incompatible is also lower and incompatible to this. So which basically means that everybody has voted either for the value in this ballot or for a ballot with a higher number. So you are fine. So at least you are sure that this ballot has been prepared correctly, in the sense that anything which is lower and incompatible for this is also lower and incompatible with something else, but that something else has been sent. So in this case, you go for the ready version. So the max ready prep, you set it to B, right? And you send ready prep. So again, the prep message is the same, but this is the ready message, max ready prep to every other node. So what is the idea? So here, instead of maintaining a Boolean state as we were doing earlier, we are only increasing the numbers of max voted prep and max ready prep. So this is like the same thing. It's like saying for a given round, I'll vote only once. In other words, that is tantamount to saying that I'll monotonically increase the round number. Which means if let's say my current round number is 10, I'll not consider any other round number which is between 1 and 10, but only something which is higher. Furthermore, if I receive a value of BU where lower and incompatible ballots are alive, then it can clearly cannot be prepared. So I will wait, right? So I will not proceed with this statement over here, but I will wait. So now again, two sub algorithms. So let's look at this. So what had we seen in the earlier version of the infinite algorithm, that once we get a vote from a quorum, which is over here, we send a ready message. So here also we are doing the same. And then we propagate the ready message, right? When we get it from a V blocking set. So here exactly we are doing the same, is just that the format has changed a little bit. So the idea is the same. You need a ballot B which is greater than max ready prep. And if every node U in a V blocking set has sent prep BU, where again this condition holds. We have seen this before. which basically means anything which is lower and incompatible with your maximum ballot which you have stored. If that is also lower and incompatible than BU which you have gotten from another node, then you are fine. So this is the same as kind of getting a ready message from a max from a V blocking set for either this ballot or something which is newer. So you can happily set max ready prep to be and just propagate the ready message. So this is just a propagate function where we are propagating the message prep max ready prep to every other node. We're just propagating the ready messages. So after propagating, we again look at delivery. So again, delivery, we have the same format that there is a max ballot B greater than max delivered prep. So this is basically saying again you deliver once per round, right? And if every node U in the quorum sends ready prep BU, where again this condition holds same ballot or a newer, then we do the same. We set max delivered prep to B and we say that this has been fully prepared. So we are not using the delivered term here, but we are saying that this has been fully prepared or we are delivering the prepared message. So we can say deliver the message. And in this case, it was a prepare message, right? So deliver the prep message. So the key idea is the same. We are not changing anything. In the earlier case, we had a Boolean variable. The Boolean variable was just saying for this tag, if you have not prepared, then prepare. If you have not delivered, then deliver. In this case, we are saying that the variable max readied prep and max delivered prep, and in this case, max voted prep, will all increase monotonically, which basically means if something has happened for one round, it cannot happen again. It's the same thing. And so this is again a two-phase process with exactly the same restrictions and limitations. It is just we maintain finite state. So as we said, we will have two functions, prepare and commit. So prepare is again federated voting on the prep message, and commit is basically the same. So it will have a very similar format. It is slightly simpler. So here the idea is if the ballot B is not something that I had voted commit for, and max voted prep is equal to B, right? So where is max voted prep set? I will show you. It is set over here in the prepare function. So look, if this is what I have prepared, then I decide to commit it. I decide to go to the next step. When I have received vote commit B from a quorum and I have not readied the commit, right? So in this case, I have not voted, and in this case, I have not readied it. Same idea. Instead of a boolean, I'm maintaining a set, right? Because the point is that I could be committing and readying many ballots corresponding to different rounds. So again, in this case, if it's not a part of it, I make it a part of it. So that is why I have the union operation over here. And once I've gotten the vote, I send a ready message. So this was again the same, as you can see, the same pattern of sending vote messages. And once you get vote messages from a quorum, you send a ready message. You send ready messages after a quorum votes. So the commit function over here is that when you receive ready commit B from a V blocking set. So this is again the propagate. So we have always had a function to propagate the ready messages. So when we receive ready commit from a V blocking set, same idea, and we have already not readied it, then we put it into the ballots ready commit set, and we send a ready commit B message to every node. So to every node, we send a message saying that just propagating the ready message. And this part is again the same. We have seen it. So in this case, we deliver the commit message when we get the ready message from a quorum and B is not a part of ballots delivered commit. So in this case, we add the ballot to ballots delivered commit, and we commit the message. And what we do is that we finally deliver it. It's the end of the two-phase protocol. So we commit the message the same way we did, like prepare. So now our job is much simpler. So the basic consensus protocol, as you will see, and again this is the finite version, actually becomes far, far, much simpler. So we initialize candidate, prepare and round the same way we were doing. We let P be the voting process. Propose is exactly the same thing where we have a candidate and we prepare the candidate. So preparing the candidate would basically mean what? It would mean going back to the federated voting of the prepared candidate where basically we do it. But how do we ensure that everything less than 8 is incompatible? Well, using the check over here that anything that is lower and incompatible is also lower and incompatible with that. All right, so that is how we ensure that the moment something is prepared, it is nothing lower and incompatible with it is actually alive. So once the ballot has been prepared, and if let's say prepare is less than the current ballot, so again this is a standard check that we have had to ensure that we prepare a ballot only once. So then what we do is if the candidate is less than equal to prepared, we set candidate to prepared. Again, we have seen this earlier and we commit the candidate. And when it is committed, we decide. So as you can see, this is the same pretty much as the algorithm with infinite resources where you prepare first. Preparing means what? Take the ballot, anything lower and incompatible. Sorry, we are using this. You kind of cancel all of them. Essentially make everything vote false. And in this case, once that is done, once you have prepared something, it becomes a current candidate. And then you commit it. Commit it basically means you make everybody agree on this value, so make it vote true. If let's say this message is delivered in our two-phase protocol, then you decide. Otherwise, you go for a timeout mechanism. And that in the timeout mechanism, both the algorithms are equivalent. It is same as the algorithm with infinite resources. See if a node, receives messages for later rounds from the entire quorum, then you set the round to the minimum value of bu.n in the quorum and you start a timer. After the timeout, you ensure that all the messages from this node has been received and then you increment the round and then you again prepare for a later round. So in the worst case, what can happen is because liveness is not guaranteed, the rounds will keep on increasing till infinity, which is fine because the FLP result in any case says that if we have faulty processes and because of that our algorithm is not converging, that's fine. It may go on forever. So now let's come to the issue of lying about quorum slices. So because we are considering Byzantine failures, nodes may lie about their quorum slices. So let us not make any assumptions about faulty nodes, not required. As long as we have an intact set that guarantees a non-empty quorum intersection comprising correct nodes, there is no problem. Even if they lie, you will see a proof in the paper, there is no issue. All of these protocols are obstruction free. This means that if the faulty nodes stop, consensus can still be achieved. Subject to bounded clock skew, but consensus can be still achieved. Key lemmas in the proof sketch, right? So how do you prove that this is correct? So I'll maybe walk you through some few key lemmas and the proofs are all there in the papers. So if two nodes in an intact set send ready TA and ready TA dash messages, then A is equal to A dash. So we have already seen this. And because of quorum intersection, this will happen because the single correct node will not lie to the quorums that it's a part of. If V1 commits a ballot B1, see if let's say node V1 commits a ballot B1, then the largest ballot B2 prepared by any other node in the same intact set, right, before the commit, right? So before you commit, is such that B1 is compatible with B2. This can be easily seen in the proof. So this I can show you. It is being ensured by this line over here. So let me maybe clear off the view, the ink on the slide. So it is this line over here which is saying that look, everybody has to have prepared for this or basically a compatible ballot which is larger. And given the fact that the other node will have to pass through this stage and this check is being done as you can see everywhere. So again, so as you can see, this check is being done everywhere. So it is not possible to bypass this check at any step, right? So that is why it is not possible that something else will get prepared and move through all the stages once some node in the intact set has gone as far as commit. So the next thing is that all the correct sets in an intact set ultimately decide the same value. Of course, if the algorithm terminates, so we have already seen different avatars of this. I will not describe this further, and needless to say, it's a proposed value. So this again follows all the properties, or let's say guarantees all the properties that an FBQS algorithm is supposed to provide. So what is the conclusion? Well, the conclusion is that we were able to kind of give a very different algorithm. But again, the algorithm is basically based on quorums and quorum slices, where of course in the intersection you need a correct node which is not going to lie. So as long as this can be ensured, we can ensure that our protocol is much faster because all the nodes don't have to participate, right? It's only a limited number of nodes need to participate until one quorum decides, right? Until at least one intact set, right? I should be more precise, and until at least one intact set decides, then we are done. Some guarantees regarding, of course, the reliability of nodes and partial synchrony need to be made, but those are not impractical guarantees, they're quite practical guarantees. And that is why the Stellar protocol is called an internet level protocol because you can really achieve consensus on a very large and wide scale. So these are the two papers. So I have primarily referenced a commentary of the original paper because I felt that the readability was much more. But the original paper is over here. You can also go to the website of Stellar and download the code and take a look at it. So that would be quite interesting. So this was a reasonably long lecture, and but also Stellar was a quite complex protocol, and it's also very new and it's very fast and scalable. So it is solving many of the existing issues that Bitcoin and Ethereum had, which was of a very low throughput. Of course, at the cost of additional assumptions, which at least to my mind are not very impractical. But I would like to encourage all of you to go and take a look at the source code of Stellar.